Hello again. Continuing our tutorial, common emitter amplifier, multi-stage, 2 stages, Q1 and Q2. We were discussing in the last one, this voltage divider, and we said that the key to finding out the voltage drops across these things is the bias right here, 1.5 volts. We came through that by this formula, and then we figured out 22.5 across here. If you have 1.5 volts across here, 24 volts is coming in. That leaves you 22.5 volts. And quickly, to just mention one last time, as you can see, the ratio of this is 15 times more. Therefore, I can estimate and say, okay, well, will give me that voltage drop of 15 times more across this to this, 1.5 volts, and this is 15 times more than this. Quickly, just visually, without any formulas. Now, once we find 1.5 volts, we know this is NPN. NPN needs 0.6 volts approximately to be forward biased to start conducting. If we have 0.6 volts over here, we can subtract it. So 1.5 volts minus 0.6 volts. I wrote it over here. Right here. So therefore, will give us 0.9 volts. 1.5 minus 0.6 is 0.9 volts. Now, that's the key also. Since we know 0.9 volts over here, we know the resistor value, we know the voltage drop across it, guess what? Ohm's law tells us if you know two variables, you can figure out the third thing. Let's go to the formula. Now, R4, 0.9 volts, we just said, is across it after the forward bias. The value of R4 was 1K. Gives us 0.9 milliamps across R4. Ohm's law. So Ohm's law tells us 0.9 milliamps goes through this resistor. And we figured out because the key was, we knew how much this was. We knew how much this one was, 0.6. We knew how much this one was left. That's the key. Now, this will give us many answers. So now, the key also is the base emitter current is very small compared to the collector current. We know that. We also know that the combination of this collector current and the base current will equal the emitter current, the total, once they join together. Remember, we're going by conventional current. The electron current also, you can go by, I teach automotive, so I go by conventional current going this way. I follow the arrow. Anyway, regardless of that point, we know that this current we just figured out is approximately the same as this current, as the collector current, because this one is so negligible in the microamps that we can almost neglect it and just deal with this current. So if we know 0.9 milliamps here, we know 0.9 milliamps is going through this also. That's another key. Therefore, 0.9 milliamps, Ohm's law tells us 0.9 milliamps times 10K. Why? Because it's resistance times current will give us the voltage. Guess how much the voltage is? Let's plug it in. Right here. 10K times 0.9 milliamps. 10 times 10 to the 3 if you want scientific notation, whatever. Will give us 9 volts across R3. Oh, wow. Now let's look at this a little. I just spoke to you about ratio, didn't I? Look at this. 9 volts across here, 0.9 volts across here. Isn't this resistor R3 10 times more than this one? Sure is. Therefore, we would expect the voltage to be 10 times more than this. Why? Because the current is the same, we just said. That's why I said you can eyeball this and approximate. Once you know this, the ratio, I know these two are the same current. This is 10 times more than this, so that only leaves by common sense that if this is 0.9 volts, I know right away, boom, this must be 9 volts. That's the beauty of electronics. How much is left at the collector? Well, supply is 24 volts. 24 volts, if I lose 9 volts across this, Ohm's law tells us that, and we just calculated it, that means we're left here at 15 volts. Okay, 15 volts here, 0.9 volts here across this emitter resistor gives us, you guessed it, 14.1 volts across the collector emitter. Bang. You just figured out. Once you figured out this bias voltage drop, you figured out all this. The beauty of electronics. Now, once you know all this, guess what? All these are the same. These are the same value resistors. So no surprise, same thing. Same thing. 9 volts across here, 15 volts across here, 14.1 here, 0.9 here. Everything is the same. If you want to figure out the current, if you want to, you can use Ohm's law. It'll give you 0.15 milliamps through here. Doesn't matter. Now, main point. Capacitor. We want a capacitor to be low impedance, almost like a short. You know, for AC and DC, a capacitor blocks DC after it gets charged. For AC, it's like a short circuit. So we came up with a value, 10 microfarads, that will give us a very low impedance or reactance at the frequency that we're going to send. The formula for that is 1 over 2 pi FC. Again, 1 over 2 pi FC. F would be 1 kilohertz. C would be 10 microfarad. You figure it out, it comes out to about 16 ohms, which is almost a short circuit for AC. Now, here comes the beauty of it. Common emitter. Now, we send in, this is positive, 2 negative. We're going to send in 100 millivolts. We're going to go over here. You don't lose too much over here. We said it's like a short circuit. Therefore, this will be amplified. This has current gain. This has voltage gain. And after that, again, not 16 ohms over here. We figured it out. It's the same value as this. We're not going to lose too much. So therefore, this will be amplified. And reverse. We have phase reversal. Very important. This will be the same phase at the emitter, but we're not taking it to the emitter. We're taking it at the collector. Therefore, this will be 180 degrees out of phase with this one, but an amplified version. Very important. Now, I'm going to end this video. Like I said, this will be part 2. I will continue to the next one. I don't like to make it too long. I might lose the viewers after that. So, thanks for watching. And again, please go to my site of my channel, Automotive Schematics by Joseph. I have much more schematics and serial, parallel circuits, common emitter, automotive schematics. I hope you will enjoy one video that you will encounter. Thanks.